Great. Okay, so I think I'm happier with that now. So let's I'm just doing this really slowly. So let's suppose that K1 is equal to 2. So is that a possibility? Well, in that case, P1 to me has to equal P, because there's one odd prime here, right? And this is going to be, this will be an even number.
Have to equal 2 then. That would have to equal 2 then.
Yeah, P1, so actually that's a good way to say it too, is this is an odd number, so your factor of 2 has to come from here. So this has to be, this obviously has to be even.
It has to be 2. Actually, it has to be 2.
Does it actually have to be 2?
Yeah. Otherwise, you have another odd number.
Yeah, because this is going to be an odd prime, right? And so you can't have, this couldn't be equal to like 6 or something, because then you'd have like 2 times 3 times another odd number. Right, so P1 minus 1 has to equal 2, and that's a contradiction right
P1
away.
has to be less than 7.
Well, actually, that's not quite. P is at least 7. P is at least 7. I don't know about P1. This is saying that P1 would be 3, and then.
And you're also trying to say P1 is equal to P.
Yeah.
Right. So then, right, P1 has to equal P, and then that's together. Those two things are a contradiction. Okay. Can K1 be any bigger than 2?
What?
Because then you get 2 odd primes.
Right. Then the left side has a prime squared. Okay, so that's immediate contradiction.
Why is P1 minus 1 equal to 2 and not just equal to 2K?
Otherwise, you get 2 odd
If,
primes.
if this was 2K, then you got 2 times K times something else equaling 2 times P, and so your P would actually have to factor. So product of 2 things. So, okay, so I think we've disposed of that. Supposedly the easy part. Then the other case would be if you had,
Why?
The other case is easier.
huh?
The other case is easier actually.
Oh, I hope so. The other case would be, I just need to think about it for a second, would be that you have one odd prime and then you have a factor of 2. I guess that's what I had written up over there. 2 to the K2 minus 1 times 2 minus 1. And this thing equals to 2P. Yeah.
Why is P1 equal to P?
Well, you got a factor of P in the prime factorization here. So both sides have to have a factor of P in them. Right? So if there's a factor of P on this side, then there has to be a factor of P on this side, but we've already said that this is just 2. Basically, you're just matching up. This has to be 2, so then this thing has to be P to make the thing come out to 2P. Okay. So is this easier?
Yeah.
I think so. I think K2 is going to have to equal 1 pretty quickly, because if K2 is bigger than 1, you're going to have too many factors of 2 on the left, because you'll have at least 1 right here, and this would be additional factors of 2. So in order to only have one factor of 2, K2 has to equal 1, which means this part isn't there. And now I'm kind of back to this proof again. Yeah. Look at the number of factors of 2. You only have one factor of 2 on the right side. So you better only have one factor of 2 on the left side. You're going to get at least one factor of 2 right there. So you can't have any other factors of 2 anywhere else. So this part is gone. And now you have what? A factorization that resembles the same form that we just did in the previous game. Yeah. So is required, reduces to the previous case. Okay. Took a little bit of doing, but I sorted it out eventually. Sort of. Okay, everybody all right with that? Okay, we're getting through a lot of good stuff here. Let me see what else I wanted to practice with you. Here's one. It might be might be good. A little bit more practice. And then I haven't really done any cryptography, I guess. But I think there's a couple of cryptography problems on the review materials, so I might let you look at that. But let me try this one out on you. So this is, what number am I on? 6? Okay, put these on top of it here. Number 6. So Lisa, did you get some good notes on the last problem?
That's why I kept asking
Asking
questions.
the details, yeah. Sorry about that, I'm giving you a tough assignment.
I'm pretty sure that I have
Got it right?
everything.
Okay, thank you very much. Okay, so here's the next problem. For n greater than 1, prove that the sum of the positive integers, prove that the sum of the positive integers less than n and relatively prime to n prove that that sum is, if you add them up, is exactly 1/2 of n times phi of n. Remember that phi of n is almost always an even number. So it may look like this is a fraction, but it really is not going to be a fraction in almost every case. Before we prove that, let me just write down an example. Let's just try an example. Can somebody give me a nice number that's not too small, not too big? 10's too small.
15.
35.
35, okay. Let's try a 35. Let's make it odd at least so that we have to think about it a little bit. So if we add up the numbers that are less than 35 and relatively prime to 35, let's see what we get. So this is going to be quite a few numbers. Okay, so here we go. So we're going to add them up. 1, 2, 3. I'm doing numbers that are relatively prime to 35 and less than 35. So 1, 2, 3, 4. And then, so keep in mind, this is 5 times 7. So anything that doesn't have a 5 or a 7 in it, we want to add up. So we'd skip 5. We go with 6. And then what? 8, 9, skip 10, right? 11, 12. Who picked this number? 13.
Laura! I said 15.
14 is, we exclude 14. We're just not adding the numbers that are relatively prime to 35.
Oh my god.
15 doesn't work. 16, 17, 18. We want to do that one, right?
You have a calculator on the test.
19, right. 21 we exclude. 22, 23,
24.
4 counts, yeah.
26.
26,
27.
okay.
29.
Oh yeah.
31.
31,
32.
32,
33.
and
34.
34. Okay, does somebody have a calculator? What is phi of 35, by the way?
24.
Yeah, it's phi of 5 times phi of 7, which is 4 times 6, which is 24. So we are hoping that the final answer is whatever that is when you add all these numbers up. Okay. That's what we hope that it adds up to. 12 times 35, right? Basically what it is. Which is, does it work?
420.
420?
Yeah, that works.
That is what it is. Okay, perfect. So it works. The question is, why does it work? Why does this work? I have no idea. It's a cool little thing. So basically, let's write down the numbers that are being added up. So for the proof, I'm going to imagine that these numbers that are less than n and relatively prime to n are listed as A1, A2, A3, and so on. So the numbers in question are A1 plus A2 plus A3. Well, actually, I just want to make a list. Not pluses, just commas. Just make a list here. All the way up to, of course, the number of numbers that we are adding is phi of n. So there should be 24 numbers, right? So we added up 24 numbers. It's just saying if you add up all of the numbers that are relatively prime to n, and the phi function of n, you add all these up, you're always going to get half of n times phi of n. Okay. So I don't know what we get for sure, but let's just give it a name. Let's let S be the sum of those numbers. Okay, let's just do that. Does anybody have any thoughts about how this is going to work? And why this works? The example is helpful. Now, in the example, I added them up from smallest to biggest. Yeah, go ahead.
Have we got the first one and the last one?
Oh, what's the first one and last one add up to? 35. What's the second one and the second to last one add up to? 35. And how many pairs of those are there going to be? Half of however many numbers you have, right? Okay, that's basically what's going on, right? So if I call this S, I could just as well, this is actually Gauss's trick for how to add up the first so many numbers, is you could add them in the opposite order, right? A of p of n minus 1. So if you were to add these numbers in the opposite order, and then just do a vertical addition, you just add them up vertically, you get 2s on the left, right? You guys seen this trick? This is a trick for how to add up 1 through n. But we're not adding 1 through n right now. We're just adding up all the numbers that are relatively prime to n. But it's the same idea, right? So these two numbers, actually, what is, okay, so what is the phi of nth number? N minus 1, right? It's just n minus the first number. So a sub phi of n, does everybody agree that's just n minus a1? It's just n minus a1.
Does that require a proof?
No, it's really clear, I think. So if you list, basically you list these numbers are not just arbitrary numbers. The last number and the first number add up to n. So what's the last number? Well, it's n minus 1.
Well, I mean the fact that the first and the last number add up to n.
Well, yeah, so I guess if I'm doing, so this was not what I meant to write here. If I add these two, I should just simply write n. Right? And the second number and the second to last number also adds up to n. And you just do this addition all the way down the line. You're just going to get n. And you get that phi of n over 2 times.
Times n.
Sorry, phi of n times. Yeah, phi of n times. There's one. There's that. That's how many columns you have. Okay, good. So 2s is equal to n times phi of n, and so s is 1/2 of n times phi of n. Yeah, that's basically how it works.
Okay. I mean, we only know that we only know that those pairs add up because of our example, or there's a
I wondered if that was going to bother anybody. Let me just. I can explain it a different way. If I write down, let's not worry how they pair up. Don't worry about which one pairs up with which one. Just take this list. Just take this list. This is all of the numbers that are relatively prime to n. Would you agree that if I take that list and then I just write down all of these numbers, what I have written there is the same list, just in a different order? The reason is that if I have a number that is relatively prime to n, if a is relatively prime to n, would you agree that n minus a is also relatively prime to n? So if this one is equal to 1, would you agree that this one is equal to 1? This actually goes back to the earlier material. You know, how do you prove that two GCDs are equal? You know, you prove that everything that's a divisor on this side is also a divisor on this side, and everything that's a divisor on this side is a divisor on this side, and that's easy to show for this pair of numbers. So if these two numbers have nothing in common, then these two numbers have nothing in common. We made that point when we wrote down, you know, when we write down the Euler, the set of numbers that are relatively prime to n. Remember I said it's like a mirror? You go halfway to n, and everything on the left half mirrors everything on the right half. That's really because of this fact, right? So because this fact is true, so you can take every single a that is relatively prime to n and replace it with n minus a, and as long as you do that for the entire set of all of those numbers that are in this list, right, then you're going to be listing all of the numbers that are relatively prime to n, just in a different order. And if you've arranged them in increasing order, you don't have to do that, but if you've arranged them in increasing order, then over here, you're just going to be doing this, looking at the same list of numbers, but in decreasing order. Yeah.
So essentially, all the numbers there are listed there.
Yeah, just in a different order. Exactly. Yeah, exactly. So this is listing them in increasing order, all the way up to 34. But I could just as well have added them. It's really what this proof is. I could just as well have added them in the reverse order. As long as you understand that mirror concept, you take two numbers that are opposite to each other across that mirror boundary, they will always add up to n. In this case, 35. Yeah, that's kind of how that works. Okay. Okay, I got just a couple more things that will be just about done. Are we all right with that? I didn't really write this up as beautifully as I'd like. I'd basically say what you have over there is the guts of the argument. This is just kind of a chicken scratch over here. All right, let's try one more thing, and then maybe I'll touch on the rest of it. Number 7. Let R be a primitive root of P. Let's show the following thing. That the index with respect to this primitive root R of P minus A is congruent to the index with respect to R of A plus P minus 1 over 2 modulo P minus 1. Let's try to prove that. That's a little bit of practice in going back and forth between an index equation and a mod P equation. Basically, mod P is the original mod, but then here we have P minus 1 for the index equation. Remember, whenever you take a congruence that involves indices, it's going to be modulo phi of n. Of course, phi of P is just P minus 1. Right, so this is a theoretical little proof here, really. And anybody have any thoughts here?
Rewrite the indice of R with P minus A as indice.
Say again, I'm sorry.
The indice of R with P minus A, can we rewrite that one?
Yeah. So maybe we should think about how we could maybe rewrite this another way, right? So how could we rewrite that in another way? I mean, we could call it something if you wanted. Call it X if you want. then that just means that R to the X would be congruent to P minus A in mod P. Is that what you mean?
No, using
No,
our
I'm sorry.
properties of indices.
Oh, you want to use the properties of indices. Okay, so you want to rewrite this one how?
There is no one for that?
Not for
Be
subtraction.
There is
careful.
no one for subtraction.
No, there isn't. There's a property for indices for multiplication, but not for subtraction. So it's sort of like, I'm thinking about logarithms. So you have this kind of property. So the log of a product can break up like this, but then if I gave you this, well, sorry, if I gave you this, right, we really can't do anything with it. Yeah, so addition and subtraction isn't really terribly well behaved, unfortunately. Did I see somebody else with their hand up?
I have the hand up.
Go ahead, Laura. You have an idea?
Could we somehow rewrite the P minus 1 over 2 as an indice of R?
Well, if you could,
Or how
then
would
you'd
we-
be able to, you'd have one index plus another index and you could combine them together. So
Right.
that's definitely a
So
thought.
my question would be, how do you rewrite something as an indice?
Yeah, exactly. So you would have to figure out what power of R that this was equal to. Right? So what do we know? We know, of course we know, and this is always true, not because it's a primitive root, but we know this by Fermat's little theorem. But we do know, sorry?
It says R is a primitive root.
Yeah.
That P minus 1 divided by 2 is also converted to -1.
Right. Do you remember this from the homework? This is from the homework. So by problem 6A, I think, in homework number 9, the one that you did for Monday, you do know that that is true. So the index of, so what's that tell you then? How can I rewrite that as an index equation? So what I'm going to do, I can just take the index with respect to R of both sides. Let's just do it that way. So this index is congruent to index of -1 modulo P minus 1. Right?
Right.
But what is this? This is like taking the log of e to the a. It's just a, right? These two functions undo each other. This is just P minus 1 over 2. I think this is what you wanted, Laura.
I think you were saying it backwards though. Because you said what power of R gives us P minus 1 over 2. That's not what we're looking for, right? When you're trying to find indice R of A, that's when you're looking for what power of R gives
So
you
if I call this the index of R of
something.
A,
Right, you would just be doing R to the P minus 1 over 2.
right? Oh, did I say that?
You
Is
said
that
it.
what I said?
No,
I'm
no.
sorry. Yeah. Basically, I'm looking for what is R to this power.
Okay.
Right, in mod P minus 1. So, okay, so I don't see how to do the whole problem yet, but I at least knew this. If R is a primitive root, I know that this is true by the homework. And then I can take the index of both sides of a congruence like that. I can always do that. Okay, we've done that many times. So if I take the index of both sides, why would I do that? It's basically to get this P minus 1 out of that exponent. So if I take the index of R to a power, I just get the power back. So that's where the P minus 1 over 2 is coming. So,
So we can rewrite P minus 1 over 2 as indice sub R.
hold on a second. Let me erase the board first. Maybe we could just like work backwards.
Because the base punches the base.
Is that what you were going to do? Tell me to do?
Oh,
So I can start from here and work backwards for a second. This is what I'm trying to prove.
yeah.
So what I would suggest then is Well, maybe we'll just, maybe not even work backwards. Let me just work with the right-hand side for a second. Let's just work with the right-hand side. So this is the right-hand side, which is the more complicated side. And in the world of mod p minus 1, this is the same as minus 1, right? So I do know that. And so, yeah, Frank?
Sorry, if you do work backwards, then can you just consider the case where p minus a is converts to negative a mod p, and then take the index of both sides, and then you get that? Or can you not do that?
So p minus a is converted to minus a mod p.
And then just take the index of both sides.
So take the index of both sides of this. You certainly can do that.
And then you do that.
And then
Okay, so this is equivalent, yeah.
But the indice of -1 plus the indice of A equals the indice of P minus.
So can I just put these together?
Yeah.
This is what I want to work on.
Yeah.
So if I put these two together under multiplication, this is one of our that's what you were telling me to do? Okay, yeah. So that's just the one of our index properties. This is modulo p minus 1. I'm trying to get the index of p minus, oh, I see, you were giving me the next step. Okay. Sorry, we're working at it from both sides here. Yeah, so we have this, but then this is congruent to the index with respect to r of p minus a, simply because negative a and p minus a are really the same number. So of course they have the same index. And these two numbers are the same modulo p. So then their indices are the same modulo p minus 1, right? Oh, that's the whole proof.
Yeah.
We're done. Okay, it does rely on this though, didn't it? We did need to remember that. That's why I wanted to do this problem, to remind you of this. So if r is a primitive root of p, then when you raise it to half of its order, it's always congruent to -1. Does that work the other way around?
No.
Right, in class I showed you the converse is not true. So just because you take a number and you raise it to a power and get -1, doesn't mean that that power is half of the order. Right, so it doesn't mean that r is a primitive root, in other words. Yeah, so, okay. All right, so that's good. I just wanted to practice a little bit on that. Well, what else did I've been trying to mix it up a little bit here. I did all that. Gonna do a group work. Let me ask you about this one last thing, and then I think I'll feel pretty good. You know, you remember when we did in class? We did the prime, I think 17, and I made this table. We found the primitive root of 17, and then with respect to it, we made this table. Because 17 was prime, of course, the x's that you're going to look at are all of the numbers that are relatively prime. Remember that when you're doing the theory of primitive roots, you're only looking at the numbers that are relatively prime to the modulus. Because when you take the primitive root and you raise it to all of the powers, so if you take r and you square it, cube it, 4th power, 5th power, 6th power, and so on, you're going to get all the numbers that are relatively prime to the modulus n. Well, if your modulus is 17, then you will get every single number from 1 to 16, because all of those numbers are relatively prime to 17. I don't know, did we ever do an example where it wasn't a prime modulus? Should we do that? Or is it?
Well, we did 10. We did number 10, and got
We
it.
didn't.
Huh?
1379, or so.
Oh, we did.
Oh,
we did.
on the homework. we did.
Yeah, so just to clarify, in general, your table might not have p minus 1 columns, right?